Hey everyone, it's Mr. Canfield. We're going to finish chapter 32 today. Or that's my goal. There's a good chunk of stuff here, even though there's not a lot left. So, I said I was going to start this video and finish the examples. And if you notice my smooth talking, I just don't want to wake up the ladies because Mrs. Canfield was up a lot last night with Maeve. Surprise. That's what happens when you have a 6-month-old. And Rosie just joined them too, so all my ladies in one place. Okay. So we're still in the at the end of last video, we had some strange ones, and he hasn't added any new directions, but he has given us these new problem types. Now we have bounds on them. So this is, just kind of rolling in from where we were before. I don't actually think I need to do this example. I'm going to, but it's kind of more of the same, right? So I see x is on the bottom and the top's just a number. I'm guessing I can just do regular u substitution, where I make the whole denominator u, and then when we do our du, we get 2 dx, and then I'll do my normal switcheroo. So I'll get du over 2 is equal to dx. So when we go in and do our substitution, I should sub the bounds out, right? Because if x is 4, what's u? If x is 4, well then u is equal to 2 times 4 plus 1, 9. What about if x is 0? So 1 to 9, we still have the 4 there. That's u, and then this is du over 2. Oh, okay, so the 4 and the 2, we could, let's do some ketchup and mustard. 2, right, because 4 divided by 2 is 2. That's not showing up well. Yeah. If only mustard didn't stain in real life like it's not staining my paper right now. That's a 2. Don't like that color either. It's too similar. So now we've got, I'll pull a 2 out front. 1 over u du. So we have 2, and then we have ln absolute value of u. I almost forgot the absolute value. From 1 to 9. So the cool thing is I don't actually have to go back and drop u back in because the bounds are different. So I can just now say, okay, this is 2 ln 9 minus 2 ln 1. And so this is where the absolute value really is important. The absolute value of 9 is just 9. So I'm actually going to drop the absolute value, because if I, we could say, I took the absolute value of 9, I got 9. Took the absolute value of 1, I get 1. But just a reminder, what is ln 1? That's one of those, we can conceptually go through it, but, kind of ask your brain really quick. ln 1, what's that? And hopefully it's spitting back something, because ln 1 is 0, because it's, e to some power gets me 1, right? So it's e to the 0 gets me 1, and that's why it's 0. So this is 2 times 0, and so it's just 0. So 2 ln 9, it actually would be our exact answer. And we can always go to our calculator and type that in. But if we're going to go to our calculator, we can go to our calculator at the very beginning here. Let me, just in case It's been a while since I've talked about this in a video for sure. Oh, there's my knee. Hey, computer. This is my super high quality. There we go. There's my calculator. I forgot to grab a calculator when I went into the building. I've been in a few times, and I've never grabbed one. And I'm like, I've got the app, and you should have the app too on your Chromebook. So I'm really helping you by showing you this, right? So just a reminder, we can go math, and we have all these options in math, and we're doing integrals. And I still remember back to when I was in high school 100 years ago. David Hamilton says the effing integral, and I thought it was the funniest thing in the world. It's not that funny, but that's why I call it that. It was either David or Brian. They're twins. All right, so, and now I can just I just drop the 0, drop the 4. Now, since this was a fraction, we'll have to be careful and put the fraction in parentheses. Oh. Specifically, I need to put the bottom in parentheses. If the top was more than just a number, I would need to put the top in parentheses as well. But the way that the calculator reads this is it says, okay, the top is 4. If the top had been a bunch of things, we'd want to put them all in parentheses. But it goes 4 divided by. So whatever we have there, it's divided by all that. Give it its variable, and let's just cool. So, and those of you with a TI-89, it should spit out 2ln9 as the answer. So, sorry if my pop socket made nasty noises. All right, let's see. So 11 is another similar one. So this is a good chance for you to kind of think about what would U be. Is it the whole bottom? Is it different things? So I'd recommend pausing the video, try a couple different U's, and if you can't figure it out, check out what I do. Right, so here we go. I know that U needs to be ln x because du is equal to 1 over x dx. And since I see the 1 over x, that's how I need to pick ln x, and not the whole bottom and not the x. So now just multiply, so x du is equal to dx. We'll go in and we'll substitute. Ooh, no. We gotta substitute the bounds too, right? So e squared is equal to, yeah, that's how you do it. So if we're using e squared, then that's ln e squared. So ln e squared, just a reminder, there's an exponent in there. We can bring it down and say 2 ln e. And if it's 2 ln e, oh wait, ln e, e to what power gets us e? 1. This is just 1, so it's 2. This is kind of fun because now the bound is just 2. Likewise for this one, if we say u is equal to ln e, oh, it's just 1. So all of a sudden we have this nicer situation. So I said my u substitution. Hey, cool. X is canceled. That's great. I got du over u. So we got 1 over u du, or du over u. And so then we'll get absolute value, or ln, absolute value of u from 1 to 2. Nice, easy. We get ln2 minus ln1. And remember, ln1 is 0, so we get ln2. really, really good example with the x and the ln x down there. Looks tricky, and then it turns out to be really nice. Sorry for slurping my coffee. All right, then 12. I really want to skip 12. I got a comment once where a student said, you were talking, and then you were like, all right, I'm probably getting confused. I'm going to stop there. And they were like, no. So I don't want to just assume everyone's good. So in this one, again, it starts to become formulaic. The bottom, we take the derivative of the bottom, the 1 goes away. So that means u is going to be 1 plus cosine. Our du is going to be negative sine dx. So du over negative sine dx, is equal to dx. And then we'll also need to kill the bounds, turn them into u's. So when I plug in pi over 2, u is equal to 1 plus cosine pi over 2. And cosine pi over 2, with a circle, pi over 2 is up top. So cosine is the x coordinate, so 0. Okay. I'm glad I did that. My brain was actually thinking 1. So our top bound is 1. And then our bottom bound, cosine of 0 is 1, so that's 2. All right, I'm going to leave those. You can switch them and put the negative out front, but I'm going to leave those just to kind of give that side of the coin. Just doing my substitution now. Negative sine x dx. Oh, no, du. I was like, wait, that doesn't cancel. Du over negative sine x. Like, if it doesn't cancel, that's our indication that there's a problem, right? That's one of the big ideas in U substitution. So there is a wait. I'm like, oh, I'm not going to bring the negative out. There's no reason. There's a negative here. Well, then we may as well flip the bounds and pull a negative out. Pretty nice, right? Negative, negative. So then we'll get ln2 minus ln1. Skipping a little bit of the steps there because it's starting to be very similar at the end. Stu really should have made number 10 also be the exact same thing, because 11 and 12 have the exact same answer. Which, if you want to pause and kind of gawk a little bit, it's crazy that 2 incredibly different situations have literally the exact same area. Not down to the millimeter, not down to the micrometer, not down to what an electron microscope could see. Literally as exact as there is, same. Not like identical twins, like more exact. I mean, if any of you know identical twins, they're the same person, right? They just put on a different hat. No, I'm just kidding. I personally love being able to tell identical twins apart. And be like, I don't know how people could say they're the same, because they're so different. Okay. So I am going to forego talking about any lead up for this. I think we'll just cover it in this problem. So I see this e to the 5x. That's my thing I'm going to be focusing on to try to figure out, but I can pull a 4 out front, right? So if this said e to the u, That's going to be really nice for us. So let's say u is equal to 5x, so then our du is equal to 5dx. So du over 5 is equal to dx. We'll go and we'll do our substitution. And I want to just state, in case everybody is following through this video, this is not the only way to do it. I had a student 2 years ago suggest solving for dx here. I actually gave them a hard time about it, but it's a really, really good way to do it. Just in case you missed it from previous videos or if I wasn't super clear, an alternative method for getting from here to here is, okay, you always want to show what u is, but getting to here is usually plenty to then be able to go, all right, well, I'm going to pull a 4 out. I mean, I wouldn't even get to here. I would get to 4/5. I'd pull the 5 out and when I write that step. So we see this. So in order to write a dx, I'm going to need to write a 1/5 du. So I know I have to have the 5th. So I actually was not taught this. My teacher stopped here and we kind of had to figure things out. And I realized, like, you don't need to. You can totally solve it. You can make it a little bit more mechanical. And honestly, now that I do this way, I really like it. But when we go to something like this, we lose a little bit of our speed, and but we gain consistency. So those have, at least in my experience, been my two big trade-offs. I can either go fast or I can be consistent. Okay. We got to talk about what the antiderivative of e to the u is, or what e to the x is. Just in case, it always looks a little bit dirty. There's lots of jokes about this on the internet. You can figure it out. All right, so e to the x. Well, what do we take the derivative of to get e to the x? Remember, that's what an integral is. Well, it was e to the x plus a constant. So the derivative of the integral of e to the x is e to the x. It's the best one. It really is. Ln x is like the second best. I mean, 1 over x is the second best. So we get 4 over 5 e to the u plus c. And since we don't have bounds, we'll just drop the u back in, 5x. We can double check it. If we were going to take this derivative, the c goes away. The e to the 5x stays e to the 5x, and 5 pops out, right? And the 5 and the 5 will cancel. So, I mean, if I'm talking about shortcuts and speed, there are definitely situations where I wouldn't even do all the u substitution for this. I wouldn't do any of the work. I would go, oh, well, that's still going to be e to the 5x, but a 5's going to pop, and I kind of work backwards. I'll actually show you what I mean on the next one before I do a u substitution version of it, because it doesn't necessarily, just because u substitution is applicable doesn't mean that we actually have to do it. So like if we think about this, well, I know if I took the derivative of e to the x squared, I get e to the x squared and x pops out. So, oh no, a 2x pops out, right? So I know that I could say, well, I'm going to end with an e to the x squared. The x doesn't need to be there, but there's a 2 that also pops out, but I don't see the 2 in the end. That means there needed to be a 1/2 here. so that when the 2x pops out, the 2's cancel and the x is still there, and now we're left with that. Yes, you are allowed to do these in your head. Now let's do the work. You know, I would imagine you don't watch my videos to watch me do stuff in my head. So I see the e to the something, so I'll say u is equal to that thing. We'll say our du is equal to 2x dx. We'll divide both sides by 2x. See, like, there is something nice about this mechanical boom, boom, boom. We do this, we go back in, we drop it in. And then, so now we've got, see, it's over 2, so I'm going to say 1/2 out front. We got a wonderful integral here, because the antiderivative of e to the u is just e to the u. And we'll drop our u back in. So I'm not going to question you if you're able to do that jump. Or like, sorry, I'm not going to mark points off if you can do that sort of thing. It's more like I am going to kind of want to see that, you know, if everybody's doing this jump, I'm a little skeptical, because I know some of you, like, your brains don't work like that. Like, you're not looking for mental tricks. You're looking for consistency, and you aim for, okay, I want to get through it. I'm not looking to be flashy. I just want to get through it. So it's kind of where if everyone was doing it, I'd be like, something fishy going on. But I wouldn't be surprised if a bunch of you were comfortable with it. Okay. So in 15 and 16, 15 and 16 are both where we make the e to the something, we make that something equal to u, and it's more u substitution, it's more practice. I look at 17, and I actually I'm not seeing it, so I want to tackle 17. So 15 and 16 are worth trying. And if you try them and you get stuck or you have any questions, feel free to contact me. I'll happily work through those with you. I'm just looking at what time it is and the other videos I have to film. Okay. So my hang up here is I can't split this into 2 fractions because the subtraction on the denominator. If it was flipped, I could do that. But I don't know what's happening with this up here. So I'm going to try making u equal to 4x. But I don't think that's the right step, because if I do that, oh my gosh, I just saw it. It's okay, I'm gonna keep going. Like if I do this, and we go back in, it doesn't really fix anything. We still have a situation where, okay, there's a 1/4 out front now. But like, I don't know this antiderivative. I don't know what to take the derivative and get that. Then my next thought was, well, what if I made it the whole e to the 4x? Well, then our du is going to be e to the 4x, but a 4 pops out, right? So So if I do that, oops, does it to you? So just drop that over there. So if I try that, I'll get, there's still, I can pull the 4th out front, but there's this e to the 4x. Oh, wait, no, that's u now. Right, and this is 4 minus u. And then 1 over, if that's e to the 4x, well, that's u. 1 over u du. So, like, I can cancel those, but it's 1/4 1 over 4 minus u du. Like, it's still not secretly, like, yeah, you could go and you could do a u substitution on this one now. Like, just, you'd have to, like, do w or something like that, or v or b. We'll pick a different letter. But, like, we're not really, it's not falling apart. So that kind of was a dead end. This is, it's not a dead end, but it's not a nice end. It's a circuitous route. What if you make the whole denominator equal to u? If you don't see it yet, that's cool. So now we divide. And we substitute. So there's a negative 1/4 out front. We got our e to the 4x is still there. Denominator is just u now. This guy is well, would you look at that? So instead of having the negative 4 down here, I pulled it up front. And now we have a perfect, oh, I gotta be careful. U and 4 are starting to look similar. There, that 4 looks like a 4. My U's are also starting to look like N's. Well, hey, so this is just going to be negative 1/4 ln absolute value of u plus c. And this is definitely a situation where absolute value is important, because when we drop u back in, we're going to get a lot of negatives, but then we'll take the absolute value from, we'll get positives. Whew. So I don't do this to throw you off. I do this because this happens. You're going to try a problem and you're going to approach it 3 or 4 different ways sometimes. And you might not recognize it. And if you were watching closely, you saw me pause. You saw me pause. You saw the moment it happened, and you can rewind if you missed it. Where, oh, I see it now. And guys, I have years of experience on this. Some of you are going to be faster than me. Others of you are going to be like, how do you get that so fast? So everyone's brain works a little bit differently. You're not stupid if you don't see it quickly. Really good example for us to look at. Then at the bottom of the page, not a whole lot worth talking about. I think 18 trips people up because it looks so silly. So I think 18 is the last one I'm going to do on this page. Yeah, so I think the place for us to go before we look at 18 is if we look at 20, look at the denominator. What's the derivative of the denominator? It's the top. 18 is the same deal. 18 looks bad, and then it turns out to be kind of silly. You might remember from AB, I told you, you're not allowed to leave negative exponents in the answer. Well, for some reason, with e to the x's, we do it all the time. So, yeah, good luck figuring that one out. We never do this, except all the times that we do. All right. If I make the top equal to u, I might... Okay, look, don't make the top equal to u. Try making the bottom equal to u first. That's usually the right strategy. du, well, e to the x turns into e to the x. Ooh, fancy. So technically there's going to be parentheses around all this before the dx, right? So this is going to still be an e to the negative x, but a negative pops out. So we don't, it's actually better for us to leave this as e to the negative x. I know in AB I harped on it over and over. You gotta flip it, you gotta flip it, you gotta flip it. With e to the x's, this is much more convenient most of the time. So when we divide, look, this is the exact same thing as the numerator. I want to stop there, but I'm not gonna. So we divide it over. We drop everything back in. This is 1 over u now. Yay! So I can say my integral is going to be ln of u plus c, and u was e to the x minus e to the negative x. Caution, we remember, like, our brain might go, ooh, yeah, there were these log rules, there were things we could do. That's when it's times or divide inside the log. Plus or minus inside the log, we don't have tricks for that. So that is, that's what's going on with the e to the u stuff. All right. Now to talk about a very, very useful trick. So there's really useful stuff in here. I'm going to skip to 23 and teach it my way and talk through it. And we are going to use our calculator for these. So 23 says, so that, hold on, let me, hey everyone, so if you jumped to here, this is our little side lesson on a really, really important feature of integrals. So if you've been with me the whole video, cool, and if you haven't, welcome. So 23 says let f of x be an antiderivative of that if capital F of 1 is equal to 3, find capital F of 5. All right, so let capital F, I need to call this capital F. Let capital F be an antiderivative of the square root of 4x squared plus 5. If capital F of 1 is 3, find capital F of 5. So, what? We look at this and it might be kind of obtuse. But remember, you know, we're doing integrals. And so these are a special kind of problem that let us kind of go around actually finding the integral. Go for it. We're gonna, in just a minute, we're gonna find this integral. So use all your strategies. Take a few minutes, try different strategies, try different things, and find the antiderivative. So pause the video if you haven't already. Find the forgot the x. If you haven't already, find the antiderivative in 3, 2, 1. 1. Okay. So if you've tried, you didn't get there. And if you did get there, I'd love to see what you got. Try taking the derivative of it. Do we get that? We don't have any strategies right now that'll give us the antiderivative of this. And the cool thing is we don't need it to be able to take definite integrals of this. So it says f of 1 is 3. Find f of 5. In this kind of problem, they're secretly telling us, well, something about capital F of 1 and capital F of 5. Well, I do know with integrals, I don't expect you guys to make this leap. I'm making this leap for you. I know in integrals, if I was to go from 1 to 5 on this, I don't know what the antiderivative is, but I do know that it's equal to whatever integral I get. You know, we could call that f of x, capital F, from 1 to 5, right? Which another way for us to write that is, I know that it's capital F of 5 minus capital F of 1. So again, I could say the integral from 1 to 5 of square root of 4x squared plus 5 dx is equal to capital F of 5 minus capital F of 1. And you're like, yeah, but I don't know what capital F is. Precisely. You don't know what capital F is, but we do know. If you're new to the video, this is because I didn't pick up a calculator at school. We do know the exact value of the integral, even if we don't know the expression. Let's see, square root 4x squared plus 5. I'm just going to double check that it's not a fraction. Okay. And then I have a little trick that I use to figure out if this is something nice. I try squaring it. Dang. Okay. Because sometimes you get like a nice number here, and you're like, oh, that's the square root of 83 or something weird like that. But nope. This is the square root of 669 point. So 25. So remember in this class. And that it's arbitrary, but we go to 3 decimal places. So 25.866. And remember, 865 or 866 are both valid. And you might be like, well, great, we found that, but so what? So the trick to these is, if I know something about its antiderivative, f of 1 is 3, and I want to find f of 5, well, hey, you said f of 1 is 3? That's really, really easy to solve now. If I add 3 to both sides, I get 28.866 is equal to f, capital F of 5. It's like to me at least, it feels a little bit like a trick question. But you know, from a teaching perspective, what we're doing here is we're trying to see what depth of understanding you have of how integrals work. So this is a nuance that integrals have, and it's a really, really useful one. This is actually useful when we do engineering and that sort of thing, because we'll know some sort of initial condition, and we might understand the behavior, but we don't understand where it ends up. So it winds up being really useful. Allegedly. All right. So, and like, once you understand this pattern, it's so simple. So capital F is an antiderivative of e to the x squared. Hey, yeah. This one right here, e to the x squared. So I don't remember if the square root of 4x squared plus 5 has an antiderivative. E to the x squared does not have an antiderivative that's a function that like we're used to. It's not any function you've ever heard of. And it's leaving my memory right now. I think it uses the Riemann zeta function. There's this really bizarre thingy that uses it. We can't find this antiderivative. But we can still do what we need to with it. So it says, this is an antiderivative of this. So it says if f of negative 1 is 2 and find f of negative 2, well then I could just go from negative 2 to negative 1. And then I know that since capital F is an antiderivative of this, I know I could just say it's capital F of negative 1 minus capital F of negative 2, and go to my calculator and plug this in and get a number, even though it's not integrable. And I heard Maeve rousing. I am going to need to go in just a minute. So I got 14 point. I got 14.989976. So if we go to 3 decimal places, that'd be 14.990. And then we said f of negative 1 was 2. So I'll subtract the 2 from both sides and get 12.990. But there's a negative out front. So I'll divide both sides by that. And I gotta run. But I hope this was helpful. Be right there, honey. Cool, yeah, the last two are very similar. So hope this was helpful. And seriously, this is not supposed to be everything. This is just supposed to be enough. So let me know what I can help you with, because that's what I'm about. Bye.